Passing the AICE Associate exam requires executing one continuous 14-step assembly line. Rather than treating each question as an isolated coding problem, you need to build a single data factory from start to finish. Your pipeline will always move through 5 distinct phases. First, you load the raw data. Then you pre-process and clean it. Next, you split and scale the data for the algorithms. From there, you build traditional machine learning models. And finally, you construct a deep learning architecture. This table breaks down those early steps. We always begin by importing the core tools: Pandas, NumPy, Seaborn, and Matplotlib. Once those libraries are active, you use Pandas to read your raw CSV or Excel file directly into a working data frame. Nailing this initial data ingestion phase sets up the entire workspace. A clean import process ensures the rest of your factory runs without syntax errors. As your data moves down the belt, you will inevitably encounter missing values. Machine learning algorithms run on strict math, and when they hit a blank hole in a dataset, they fail to compute and the entire process stops. To prevent this, you use basic Pandas commands like fill_NA. This allows you to patch those holes by replacing missing variables with the column's average or median value, restoring the structure of your dataset. This illustration explains another crucial pre-processing step: categorical encoding. Algorithms cannot read text like male or female. You have to translate every text category into strict numerical values so the model can process them. For this, you will often use Pandas one-hot encoding via the getDummies function. Notice the drop first equals true argument here. You must include this to prevent multicollinearity, which happens when redundant columns confuse the model's logic. By patching the missing holes and translating all text into numbers, you deliver perfectly clean, numerically encoded data to your algorithms. This diagram outlines the critical train-test split. Before doing anything else, you must separate your input features, the X, from your target answers, the Y. Then, you divide them into an 80% training block and a 20% validation block. If you are solving a classification problem, look out for the stratify parameter. Setting stratify equals Y ensures that your training and validation sets maintain the exact same proportion of class labels. Once split, you need to scale your data. This chart shows how variables with large numbers can drown out variables with smaller ones. Scaling shrinks everything down to uniform mathematical weights, stabilizing the training process. This is where many test takers lose points. You must use fit transform on your training data to learn the scale, but you only use transform on your validation data. Fitting the scalar on your validation set causes data leakage. It lets the model peak at the test it is about to take. Maintaining this firewall keeps your predictions valid. This code snippet shows the standard rhythm for machine learning algorithms. No matter which model you choose, the process is identical. You define the model with its hyperparameters, you fit it to the scaled training data, and you run a prediction on the validation data. Double-check your exam instructions here. If you are predicting a continuous number, use a regressor. If you are predicting a category, use a classifier. Swapping these will crash your pipeline. The final phase involves deep learning. This diagram illustrates how we use the Keras sequential API to build a neural network. You are stacking dense layers on top of each other to pass data through multiple layers of calculation. Before looking at the code, think about a binary classification problem, where the answer is either a 1 or a 0. What should the final layer's activation function and the compiler's loss function be? For a binary outcome, your final dense layer must use the sigmoid activation function to output a probability, and your compiler needs to use binary cross-entropy to measure the error. Matching your architecture and loss functions precisely to the problem type ensures your network learns correctly and outputs a valid prediction. The final challenge on the exam is handling a completely new set of simulation data. This dataset must pass through your established pipeline without retraining any of your models. This panel outlines the exact process. Just like with your validation set, you apply your previously saved scalars using only the transform command. Your deep learning model will then output raw probabilities. You apply a simple NumPy where function to act as a threshold filter, translating any probability of 0.5 or higher into a solid 1, and everything else into a 0. Here is the entire pipeline categorized by library. Pandas handles the data loading and cleaning. Scikit-learn manages the splits and the machine learning models. TensorFlow handles the neural network architecture. Executing this chronological sequence ensures your data stays clean, your models remain untainted, and you secure a passing score on the AICE associate exam.